And let's get into it. Some new reactions here. All right, continuing on with section 20.5. Now we're going to get into some new reactions, brand new today. So we talked about the reduction of an ester using lithium aluminum hydride and a carboxylic acid with lithium aluminum hydride. This goes back to chapter 12. We actually covered this reaction then. And the reason it shows up again in this chapter, obviously, is because you're starting out with a carboxylic acid. That's one of the main cruxes of the chapter is looking at carboxylic acids. But I want to show you a new way to reduce a carboxyl group using a reagent that you've seen before. You've never seen it used this way, probably, and that's using borane and THF. So you can actually use borane and THF. There's no second step. It's just one step. Borane and THF mixed together, and you can reduce a carboxylic acid to a primary alcohol. And the reason why we teach you this reaction is because it's what we call chemoselective. Okay, so chemoselective for a carboxylic acid. What that means by chemoselectivity, it means it's going to react with one functional group, but it's going to leave other functional groups that you might think would react with it. It's going to leave them unscathed. And so it says here in the next bullet point, chemoselectivity of the borane allows for the reduction of a carboxylic acid in the presence of an ester. But I'm going to add to this. It means you can reduce a carboxylic acid in the presence of an ester, aldehyde, or a ketone. Any one of those, okay, are going to remain completely untouched. So I'll even box it in here for you. And we'll put untouched by BH3. Okay, it doesn't have any effect on those. And so if you take this compound here, so this would be para-acetyl benzoic acid, you treat it with borane and THF, you see that the ketone, right? Remember, I said a ketone is not going to be touched, so that remains untouched. But the carboxyl group, right? The carboxyl group from your carboxylic acid, that gets reduced to a primary alcohol. So pretty cool reaction and pretty cool reagent, I should say. Now, there's no mechanism in the textbook for this reaction, none at all. So obviously, I'm not going to ask you that in any way, shape, or form. So I know that we've already gone over a bunch of content, and I kind of saved this for after the break, this one reaction. But let's see if we can come up with some reagents to do these transformations here. And remember, like I've told you several times, that as the class progresses, we're going to see more and more ways to do the same, to affect the same transformation. So what I'm going to do is I'm going to go over to a blank document just in the interest of space. And of course, I chose the wrong one, so just bear with me here. So it was here. There we go. So this is, again, this is question 20.11, 20.11, and this is A. So we're starting it with bromobenzene. That's this compound. And we want to make, this compound is called benzyl alcohol. So this is called benzyl, I'll write it down here, benzyl alcohol. Come on, alcohol. There we go. And the reason I give you that name is because benzyl alcohol comes up a whole bunch of times. It's even in the second problem. So we're adding one carbon, right? We're starting out with 6 carbons and we're ending up with 7 carbons. Did anybody come up with a strategy for this one? Has anybody looked at this one at all? There's a couple of things that you could do here. Anybody come up? What about using a green yard, right? Because we could convert the phenyl, right? The aromatic ring, we could convert that into a good nucleophile. So what if we just treated this with magnesium and diethyl ether, right? Then we're going to make phenyl magnesium bromide. So let's write out phenyl magnesium bromide. So that's this, okay? And now we just need to treat it with some kind of electrophile. So we could treat it with something like carbon dioxide and then follow it up with H3O plus acid, and that is going to give us benzoic acid. And then we can reduce this using borane and THF, or you could use lithium aluminum hydride if you wanted to. I'll put here, step 1 would be LAH, step 2 would be H3O plus. Either one of those works. Now, somebody asked me in the chat, or no, they deleted the question, okay? But I would say there's other ways to solve this problem as well. Could you use cyanide and ozonolysis? No, you can't do that. You can't use cyanide because you can't do an SN2 reaction on this carbon, right? This carbon is sp2 hybridized, so you can't do any kind of SN2. Does that answer it? Okay. All right. I'd say another option is, besides CO2 as an electrophile, if you made the phenylmagnesium bromide, you could also treat it with formaldehyde, right? In the first step. And in the second step, you could treat that with H3O plus, because this is going to act as a good nucleophile on here, right? And then you're going to end up with benzyl alcohol that way too. I would say that would work as well. I don't see any problem with it. So I would accept either way. And of course, either way to do the reduction, you could use borane and THF or LAH. Either one is completely acceptable here. Let's try another one. And this one is very, very similar. I mean, so similar it hurts. So let's put here. So this is 19, or sorry, this is 20.11. I still got chapter 19 on the brain. So we're taking toluene, and we want to, Tiana, let's use your method to do this one. So we want to take this and we want to make benzyl alcohol. Now, do we know a way to take this toluene molecule and convert it into benzyl bromide directly? Benzyl, so this compound here. So if we want to make, yeah, so that's one option. Yeah, Maria, that's definitely an option. So what Maria is saying is, Mr. Dion, what are you doing? She's saying, why didn't you just do this? Right, just do a benzylic oxidation. So Maria, I'll write your pathway down here. All takers welcome, right? So let's put that down here. I like the way you think. So let's scribble that down. Looks like this. Yeah, I would accept that. Right, and then you would just reduce using borane and THF. That will work. Zoink. Yeah, keep it simple, right? Anyhow, what about yeah, so if we have the benzyl alcohol, or sorry, the benzyl bromide, which we could make using NBS, right? Then we would just do an SN2 with sodium hydroxide. That would work too, right? They're both two-step methods. They both work. Don't have any kind of problem with either of them. We'll put here, both are good, right? They both work perfectly fine. Okay, give me a thumbs up if you see both of those methods, the Maria pathway and then the my pathway. Okay, great, awesome. Maria, now you have your own name reaction, the Maria way of doing things. All right, and then if you're thinking, well, I don't like this way of doing the benzoic oxidation. I want to use potassium permanganate and then acidify. That's fine too. There's nothing wrong with that. Either way is perfectly acceptable in this class. Okay, so let's move ahead here. Just bear with me. Let me find my slides. Where were we? I lost my place now. We were down all the way down here somewhere. And we were right here. Okay, so we solved these problems. Now we're in section 20.6. I'm going to warn you ahead of time, section 20.6 is a bit of a heavy section. Okay, it's a chunky section. Why? Because it deals with all these functional groups, and it deals with a whole holy host of nomenclature rules that we have to go over. Okay, so I'm going to try to do a slow, methodical approach to get through this thing. And something that you might have noticed, excuse me, when we do the reduction of a carboxyl group to an alcohol, it involves a change in oxidation state of the carbon. So if you remember, we went over oxidation state in chapter 12. So this carbon, right, if you break all these bonds heterolytically, you have R, and then you have the carbon, there's each split an electron. And then the oxygen here takes every single electron, and this oxygen takes every single electron. So all you're left over is with a carbon with one electron. And so you take 4 minus 1, and that gives you positive 3. So the oxidation state of this carbon in the carboxylic acid is plus 3. The oxidation state over here, if we look at the central carbon, we have 2 hydrogens. they don't take any electrons, so the carbon gets 4 from each one. It splits them with the R group, and then the oxygen gets both of the electrons from their bond. And so you have 5 electrons surrounding the carbon. So you've got 4 minus 5, which gives you -1. So the oxidation state of the carbon in the alcohol is -1. So you've gone from +3 to -1, right? So gain electrons, reduce, right? Oil rig, right? Reduction is gaining electrons, okay? So that shouldn't be anything new to you. But what we're going to look at now is that there's many reactions in organic chemistry where carboxylic acids don't change their oxidation state at all. In fact, if you have a carbon, okay, that's attached, that has 3 bonds to atoms that are more electronegative than carbon, it's going to have an oxidation state of +3, okay? So when is it going to be +3? It's when Z is equal to either chlorine or nitrogen or oxygen, right? It's always going to have a +3 oxidation state in those cases. And of course, it was +3 in our carboxylic acid. So there's no change in oxidation state here. So what are the most common carboxylic acid derivatives? Well, the ones that you have to know are going to be an acid halide. And of course, this one here is actually an acid chloride. If you wanted to be more specific, there's also acid bromide, acid iodide. Right, then we have an acid anhydride. So an anhydride, it kind of looks like, right, if you had 2 carboxylic acids, and we'll talk about this reaction later on. If you had 2 carboxylic acids meeting on the street and you heated them up and they lost water, right, anhydride, right, loss of H2O, then you connected them together like this. That's where the word anhydride comes from. So an anhydride, then an ester. I know you all know what an ester is, and an amide. I know you know that too. Even a nitrile, right? A nitrile has 1, 2, 3 bonds to a nitrogen, which is more electronegative than carbon, and therefore it's considered a carboxylic acid derivative. So acid halides, acid anhydrides, esters, amides, and nitrile, and we are going to cover the nomenclature of all of them. All right, every single one of these. Again, if you're wondering, is the oxidation state +3 here? Here it's +3. Here it's +3. Here it's +3. And then here, you guessed it, +3. All right, so let's get into the whole, idea of where you might find some of these compounds in nature. Well, the first thing is the acid halides. So if you have X is equal to chlorine or bromine, right, those are pretty rare. Or in fact, they're not even stable. So we don't really find those in nature. The same thing with an anhydride. These are really reactive. So we don't see those in nature. However, esters and amides, oh, hot diggity dog, do you ever find those in nature? Everywhere, right? If you like the smell of anything fruity, like pineapples, bananas, pears, cherries, oranges, that will come from an ester. So bananas in here, right? Isopentyl or isoamyl acetate is the same thing. Yeah, so if you're wondering, why can't we make more of these things in the lab? There is a lab that we've done before with the nursing students where we do make esters and they get to do a smell test on them and like, oh, this one smells like spearmint. This one smells like butter rum or cherries or something like that. But esters have a fruity smell, so they're fun to work with sometime. Anyhow, let's see. Let's just move on from here. And so let's talk about naming an acid halide. So the way that we name an acid halide is we replace ic acid with il halide, or if it ends with oic acid, we replace it with oil halide. Okay, so let me show you some examples here. If you have acetic acid, it's acetyl bromide, right? You replace il and then bromide. If you have benzoic acid, it becomes benzoyl chloride, right? You replace the ic acid with il chloride. And if you're wondering about the oic acid thing, let's say you had something like, I don't know, 1, 2, 3, 4, 5, 6, 7. Let's say you have something like this, okay? So this is 1, 2, 3, 4, 5, 6, 7. Yeah, so this would be heptanoic acid, heptanoic acid. If you make the acid chloride, 1, 2, 3, 4, 6, 7, right? this becomes heptan oil. I keep doing that. Heptan oil chloride. All right, so we replaced oic acid with oil chloride. Anyhow, if it ends with carboxylic acid, like if your carboxyl group is attached to a ring, you replace it with carbonyl halide. So carbonyl chloride, carbonyl bromide, etc. This is a rule that the only way I can help you out with this is you really got to memorize this rule. It might be worth the value of one question on your quiz or something like that. I've never seen it come up on a final, but yeah, this is one that can be tricky for students to remember sometimes. All right. Another one here that I was just going to point out is going back to the whole common name, right? Acetic acid is a common name. If you write down the systematic name of acetic acid, right, you should know it's ethanoic acid. So the way you would name the acid bromide would be ethanoil, right? Ethanoil. I keep doing that. Ethanoil bromide. Okay, so oic acid becomes oil halide like that. Okay, so that covers acid halides. What about anhydrides? What we do is we just take the name of the parent acid and then we put anhydride at the end. So if you take acetic acid and you make the anhydride, it becomes acetic anhydride, right? Because this side has 2 carbons in it, right? And you can see that both sides here have 2 carbons, so it's acetic, right? This is an acetyl group here. If you take a dioic acid and you make the anhydride, right, succinic acid becomes succinic anhydride. Excuse me. And then if you have an asymmetric anhydride, you list the acids in alphabetical order and you follow them up with anhydride. So we have the derivative of acetic acid here. So this is the acetic portion. And then you have benzoic acid. That derivative is over here, so benzoic. And then we put anhydride as the suffix like that. Naming esters. Another thing is if you're wondering, what about the systematic name for this one? I can't remember the last time I've ever even seen that in my life. Okay, so we always use common names for the diacids. So don't even worry about that. The next one is when you're naming an ester, you name the alkyl group portion first. And that the alkyl group is the portion that's attached to the, let me see, oxygen. I'll put here the sp3 hybridized oxygen, followed by the carboxylic acid's name with 8. Okay, so if you have acetic acid, this becomes ethyl acetate, right? You start with the R group, right? The alkyl group, so ethyl and then acetate. And of course, right, we said that this is ethanoic acid. So if you use the systematic way, it would be ethyl ethanoate. Ethanoate. So you can see why common names are common. They're used a lot, right? Malonic acid becomes diethyl malonate, right? And I would never even use the systematic name for that. I don't even have it in my notes. I would never use it. Okay, nobody would ever use it. Same thing applies if you have an ester connected to a ring. So we have cyclohexane carboxylic acid. So we name the methyl group first. Maybe I should circle that in blue. So we have methyl cyclohexane carboxylate, right? Okay, so that's how you name an ester. Then for an amide, we replace the suffix of ic acid or oic acid with amide. So either one. If it's ic acid or oic acid, we replace it with amide. So if you have acetic acid, it becomes acetamide or acetamide, depending on who you're asking, right? We know the systematic name is ethanoic acid. And so the systematic name of the amide would be ethanamide, right? Then benzoic acid becomes benzamide. If you have the amide attached to a ring, it becomes a carboxamide, so cyclohexane carboxamide. That's a rule that you just kind of have to stick in your brain, okay, the whole carboxamide thing. What else? If you have an amide, so remember that if you have an amide, so let me just zoom in here. If you have an amide and you have 2 hydrogens attached to the nitrogen, that's a primary amide. If you have 1 R group attached to the nitrogen, like this, okay, that's a secondary amide. And if you have two R groups attached to the nitrogen, yes, that's a tertiary amide. So those are the three types of amides that we can encounter. And so if you have a secondary or tertiary amide, you have to find a way to label the R group. And so if you have one R group, you put N, capital N, and then you name the alkyl group. So N-methyl, right? It's N-methyl acetamide. Or you could also call this N-methyl ethanamide. Ethanamide, that would be acceptable too. And then if you have a substituent twice, or if it repeats itself, you say NN and di. So NN dimethyl acetamide, right? Okay. So there we go. So that covers secondary amides and tertiary amides. Let's move on from there. What about nitriles? So let's see here. Oh, there's one rule that I want to go over with you here that it's not covered on this slide. And that's if you have two groups that are different. So let me just draw a little line here. Okay, put something like this. Okay, so let's say you had this compound where you have your acetamide. Okay, but now you've got a methyl group and an ethyl group. You put the two alkyl groups in alphabetical order. So you go from A to Z. Okay, so alphabetical order. So this compound would be N-ethyl, N-methyl acetamide. Acetamide. Or you could call it N-ethyl, N-methyl ethanamide. Or ethanamide. But you put the two alkyl groups in alphabetical order. That's how you do it if you have two different groups. So going back to the nitrile thing, if you have a nitrile, you replace ic acid or oic acid with O-nitrile. So acetic acid becomes acetonitrile. And this is a very commonly used solvent. So this would be ethanoic acid. So this would be ethanonitrile. So ethanoic acid. This becomes ethanonitrile, oops, nitrile, like that. Ethane, I guess you would, I don't think you would have the E in there. Benzoic acid becomes benzonitrile. And that covers all of the naming. And I know I went over that pretty quickly, but there's a lot of it in there. And so what we have to do next is cover the names of these compounds. Okay, so we're going to look at all these different compounds and we want to name them. So in the first one, we have an anhydride. So this is an acid anhydride or an anhydride. The next one has an amide. Right, it's a tertiary amide, as a matter of fact. The next one is an ester. So it's a diester. The next one is an amide again. And you've got two different R groups. The next one is another ester. And the last one has is an anhydride as well. Anhydride. So what I want you to try to do is try to come up with a name for each one of these. E is a nitrile. So this is a nitrile here. So I want you to try to come up with a name for each one of these. And for anything that you can come up with a systematic name and a, actually, I'll tell you which ones. So I want you to come up with a systematic name and a common name, or we'll do A, D, E, let's do F, and we could even, yeah, G. We'd never use the systematic name for that. Okay, so for those ones, see if you can come up with both the systematic name and a common name. And then for the next one, students are usually pretty quick at these because you're just drawing the compound and they give you, the parent is given to you and everything. So there we go.